So in this topic, we're going to talk about waves and directly relate them to the idea of sound. So sound is actually the vibration or the oscillation of air molecules. So it is a wave, and in particular, it's a mechanical compressional wave because it's mechanical because it requires a medium, and it's compressional because the particles bounce off one another and move parallel to the wave travel. So if you think of the idea of a tuning fork or a subwoofer, a tuning fork works by vibrating the air molecules in between. If you knock it on something, and you actually use this in the lab that you're going to do in this topic, to vibrate the air molecules and generate a note. Over here, if you've ever been to a concert and you've stood up close next to the subwoofer, you can actually see this move in and out, and if you're close enough, you can feel sort of a wind coming off of the subwoofer because it's moving the air molecules to generate the sound. Now, sound propagates or travels at a certain speed at room temperature, which I said was about 340 here. It's listed at about 343 meters per second. That's 767 miles per hour to sort of give you a perspective, which is a lot slower than the speed of light. Speed of light is 3 times 10 to the 8th meters per second, so it's a lot faster, which is why you see lightning before you hear it, or you hear the thunder. Now, we also talked about the fact that temperature can affect the speed of sound, and this is because the warmer air is, the faster the air particles are moving, and if they're moving faster already because they're warm, then they're going to transmit the sound energy faster. So we could actually calculate that by taking 331 meters per second plus 0.6 T, where T is the temperature. So this adds a little bit of velocity to that, and that T is should be in Celsius. Now, the pitch of a note that you hear actually relates to the frequency of the note. So the frequency is the pitch or the actual note that you're hearing. So like you may have heard of like tuning an instrument to like A440. Well, 440 is hertz. It's the frequency, and that's the note A. And we'll talk about that a little bit more when we talk about music. But someone who can hit a very high-pitched note, we know that it's very high up on the scale. It has a very, very high frequency. A low-pitched note has a low frequency or a long wavelength. Now, your voice can create sound by basically pushing air through your vocal cords in an opening, and your vocal cords will open and close and change size and affect how quickly air is moving through there, and therefore the frequency of the note that's being projected by your voice. Now, you've probably done this before, I've heard somebody do this before. If you breathe in helium and then start to speak, the speed of sound in helium versus air is a lot higher, and that's why the note moves faster and the frequency is higher, and you get a higher note. Now, sound is a wave, so it transmits energy. And in terms of sound energy, we use the word intensity. Intensity really relates to the idea of amplitude of the wave. So the higher the amplitude, the louder it's going to be. So an amplifier is actually designed to take a note and just add energy to it. It doesn't change the frequency of the note because that would actually change what note you're playing, either to a higher or lower note, but it just adds sound intensity, so loudness. And we measure loudness, and this really isn't a physics measurement, but it's an idea of human perception of sound intensity. So you may have heard of decibels, but we don't really use the decibel scale in here, but it's commonly used like if you look in literature and things like that, or you read an article, although it's not really a physics quantity. So you can see, just to give you a frame of reference, 10 decibels is barely audible, you can't hear it all. A rock concert or a jet engine is like 110 to 140 decibels. Now, we know one of the properties of, or two properties of waves are both diffraction and transmission. So diffraction is simply that sound or waves bend around a barrier or an obstruction. So that's just the idea that if you're standing around the corner, or say you're standing outside a doorway, you can still hear someone talking from inside because the wave will transfer and bend around the obstruction or through the door around the corner. And the way that sound waves are transmitted, they transmit by coming in contact with a surface, and then the molecules will transfer their energy to that surface. So this is how your ear works. Your ear works by absorbing energy. The air molecules will transmit their energy to the tympanic membrane or your eardrum, and then they communicate that information to your auditory nerve that goes to your brain, and so we can decipher different sounds. So our ear is like a receiver. Now we have a limitation to our hearing. We can hear within a range of 20 to 20,000 hertz typically. And as people lose their hearing, they can lose it in two ways. They can lose the ability to detect intensity, so very quiet or very loud sounds, but they can also lose their ability to detect a range of frequencies, so very high or very low sounds. You may have heard of the note that you can play that teachers can't hear through your cell phone, a very high frequency pitch. Well, as you age, you tend to lose the range of frequencies. Now, there's other terms that are used to describe relative velocity compared to the speed of sound. And this is the idea of using Mach speeds or supersonic and hypersonic. And supersonic just means that something's traveling faster than the speed of sound, so 767 miles per hour. And Mach speeds tell you by how much faster. So if you're going Mach 2, it's 2 times the speed. Mach 3 is 3 times the speed. And Mach 5 is actually considered hypersonic, which is 5 times the speed of sound. And when you do this, you actually generate a whole bunch of air molecules that come off of the surface that actually run into each other because they're moving faster than the speed of sound, and they collide and create what is called a sonic boom that you can see here. Now, the term ultrasound, this is a sound that is above the level of human hearing, but we can use it we generate waves they're pretty small, so they can penetrate tissues, and they can bounce off solid surfaces. So you can see here an ultrasound of a baby. The baby starts to form like more dense cartilage and bone in the skull and in the spine first. So that's where we can see actually the outline of the baby's skeletal structure. Infrasonic then is the term that we use for a sound that is lower than the range of human hearing. So like Michael Myers is so quiet that he can sneak up on you and you can't hear him. All right, the last property that I'm going to talk about other than diffraction and transmission and propagation is the idea of reflection. So sound waves will bounce off a surface and reflect back, and there's a lot of practical applications for this. So this is what an echo is. But also we use sonar in order to map the ocean floors. So we can bounce or ping a sound off the bottom of a boat, and it goes down to the bottom of the ocean and then pops back up, and we can determine the distance that it has traveled based on how quickly it returns to the boat. This is also used by animals, and even there are some people who have are blind that use echolocation and sonar in order to detect their environment around them. There's a really cool video on YouTube. If you look it up, it's called Bat Boy. I'll post it on the Twitter. But it talks about a boy who used echolocation because he was blind. So those are some properties, or how wave properties pertain particularly to sound.